Okay, I want to talk a little bit about RREF, which hopefully you've seen appearing throughout the chapters. And it just basically stands for, actually it does stand for row reduced echelon form. Right? So it's simply a way of programming row operations into a computer so that you can use it. So if you remember back in chapter 1, you just had equations, system of equations, and so you just did operations on the equation to eliminate variables, and Gauss just said, oh, why bother with all the manipulation of the equations? Why do I keep writing the variables over and over again when I can just write this as a matrix product and then just do row operations on the matrix? So this kind of situation, which now hopefully you've been well familiar with. And all that's going on is that we've abstracted this idea into a matrix multiplication times a vector, right? And we have a resultant vector. So we've recast the problem into a transformation, in this case from R2 to R2, right? And we've tried to determine, is this vector B in the range of that transformation? Got my little 2 there. So one way to solve that was to find the inverse, right? If this was a nice transformation that had an inverse, then that told us that we could find the vector in the domain space as the inverse of the vector in the range space. And then we went on to say, well, this can get messed up a little if we don't have an invertible matrix. In other words, we've got our domain space here, and our transformation, and a lot of the transformation goes to 0. Whoops. And so that was the kernel. So this should just be 0 here. 0 vector. So that was the kernel of the transformation, which was actually a vector space back in the domain area. So what I want to do is look at how that RREF got programmed and how we can use it to solve things. So here's our good old friend octave, right? And so I've defined a matrix A here, right? And of course if we want to, we can do things like just actually ask for the rank of a matrix, and it's full rank 4, so we know it's invertible, so we can just find the inverse directly, right? But we can also look at just making a matrix which is A and then adjoin the identity matrix, row reduce that so that A is reduced to the identity matrix, and then the identity matrix on the adjoining matrix becomes the inverse. So we can try that also. So here's the matrix. I called it C, which is really just A and then the identity matrix put on it. So if I row reduce C, right, and compare that with the inverse of A, right, I get the same thing. So we notice this is just the same as the inverse here. But notice one thing: if I let B equal the inverse of A, and I multiply A times B, notice what happens. I get some little negative zeros in here, right? 0 is 0, but somehow it put it as negative 0. Basically what's happening is the difference between row operations and the command that does the inverse. The command that does the inverse is actually a numerical method, which we'll get into once we get into determinants. And so what really happened here is that there was some numerical error that got rounded off to 0, but it was like, negative blah 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 blah, and, something way out there and got rounded off. Right? So there's some other things going on there. If I define B out of the, if I look at my inverse that I got before, right, then if I just write it in, and then I do A times, which is just entered from the row operations, right, then it comes out nice and neat. So keep those kind of things in mind, that these programs sometimes use direct matrix operations, because row operations can actually be written as a product of matrices, and so those can be programmed in fairly easily, whereas some other operations like inverse are actually numerical operations. So keep that in mind. So let me go back to row reducing things here. And let me stop here.